Our next talk up is from Douglas Natelson, who's going to be speaking about suppressed shot noise in strange metals.
All right, I hope you can all hear me. And I will get my little laser pointer thing working. Thank you, everyone, for sticking around, and thank you for the opportunity to present this work. I know it's been sort of advertised by two of my colleagues earlier in the session. So I'm going to talk about some noise measurements, and let me just, all right, deal with a little Zoom issue there. Okay. First, the acknowledgements. I want to make sure to thank everybody. The main driver on the experimental side was my student Liang Chen, who took most of the data, helped out by a fellow student, Dale Lauder. There's some supporting theory work that was done by Chi Miao and his folks, and of course Silke and her extremely talented colleague Lucas did there was a lot of work on the growth of the material without which we never could have done this work. So the result I'm going to talk about is available on the archive in a recently updated form, and the theory supporting work is also available on the archive. So very brief outline, and I know we're all a little bit pressed for time, so I'm just going to plow through here and start talking a little bit about Fermi liquids for the students in the audience. We kind of know what a Fermi gas is, right? You have non-interacting fermions in a box, and you talk about the lowest energy state these things can be in, and we think about a Fermi C. Here we are in 2D or in 3D. The low excitations of this collection of fermions, if we've got no interactions going on here, are particles and holes. And the particles and holes have, they've got charge of magnitude E, they've got spin 1/2. And if you do kind of Drude-Lorentz type or Drude-Sommerfeld type approach to this, the resistivity at low temperatures of a solid where the electrons obey these properties, there's some residual resistivity set by the dirt in your sample. And then at the low temperature end, there's a quadratic in temperature piece that has to do with electron-electron scattering of these particle excitations. The heat capacity goes linearly in T, the electronic part. And so if you turn on interactions, we all know there's kind of this standard theory of metals that we have. Let me see if I can actually see let me turn off the laser pointer for a sec so I can actually see what's going on in the chat, just to make sure I'm not missing things. Okay, so Landau Fermi liquid theory is the standard picture of metals. You can turn on interactions, and the Fermi surface is obviously grossly exaggerated, but there's a one-to-one mapping between the non-interacting situation and the interacting situation. And again, now the low energy excitations of the system are quasiparticles. They have a finite lifetime, but parametrically the width in energy of the quasiparticle excitations ends up being smaller than kT. So these things are actually distinct from the Fermi C. Once again, you have resistivity going quadratically with temperature, even if the quasiparticle effective mass, for example, is greatly renormalized. And again, you have heat capacity going like T. So what happens when Fermi liquid theory fails? You've already heard in the session this morning about examples of so-called strange metals, right? Fermi theory can break down when the interactions are very strong. I'm not going to really talk about the cuprates, but again, you've heard a couple of different talks this morning about ytterbium rhodium-2 silicon-2 as a quantum critical strange metal. And in this situation, in this quantum critical fan, resistivity is linear in temperature rather than being quadratic at the low temperature end. There appear to be different scattering mechanisms for rho XX and rho XY. There's logarithmic corrections to the heat capacity. And basically, the question is, are there well-defined quasiparticles here at all? And how would we tell? As an experimentalist, I always consider it a bit of a challenge when some theorists throw out very exotic interpretations of what's happening involving holography and black holes and anti-de Sitter space and so forth. And the question is, what experiment can I do that will really give me microscopic information about whether quasiparticles exist and in what sense they exist? So again, here's the specific example of ytterbium rhodium-2 silicon-2, where there's this at very low temperatures, at zero temperature, there's a quantum critical point, and you go between this anti-ferromagnetic heavy fermion system. And at high fields, after you go through Kondo destruction, you have this paramagnetic heavy fermion system. But these are both supposed to be Fermi liquids, but there's this quantum critical fan. And, how do you properly think about these things, right? So the experimental probe that we've been working on for a number of years in my group is noise. And let me give you the very brief intro to shot noise as a measurement technique. So the theorist fantasy, I like to say, is that you'd love to know the arrival time of every electron if you do a transport experiment, because then you know everything. You can do full statistics on how the electrons are behaving in time and learn all sorts of things about correlations. You can't do that usually, but you can usually do better than just current as a function of voltage. So Schottky in 1918 was worrying about this problem in vacuum tubes and thinking about, suppose I just have Poisson distributed electrons that are traversing my vacuum tube. What are the current fluctuations caused by the fact that there are just statistical variations between the arrival times of the electrons? And if you do the math, you find that per unit bandwidth, so you can kind of Fourier transform yourself into frequency space, you find that the current fluctuations are related to the average current by twice the electronic charge, if you've got a Poisson distributed arrival of electrons. Now, if the arrivals of the electrons are not independent, so if somehow they are correlated with each other in some way beyond just having an arrival rate, more generally, what people do is they cast their measured current fluctuations in terms of a phono factor, which is a relationship, the ratio between the measured current and twice the electronic charge times I. And now, just to give you a sense of what's going on here, and I hope this will play properly, you can imagine the same amount of charge traversing the system per unit time in different ways, right? Think about rain hitting your roof. The same amount of water per unit time can hit your roof either as a few randomly distributed huge raindrops or as a fine mist. And so I hope people can hear that. There's some clicking associated with the discrete arrivals of, say, big blobs of charge. But then you can imagine having smaller blobs of charge coming more frequently and having the same average current. And then you can imagine having really fine mist of charge, right, where the current fluctuations are now a lot smoother because the individual charge carriers carry less charge, right? So shot noise tells you something about the in certain experiments, it can measure the magnitude of the tunneling charge. That's not exactly what we're doing here, but that's the idea. And so if you do tunneling measurements, for example, if you make like a tunnel junction, you can measure the noise, and if you write it as a function of current, what you find is at the low current limit, everything goes back to Johnson-Nyquist noise, just thermodynamic fluctuations. So you can't honestly learn much of anything about the nature of the charge carriers at zero bias in equilibrium, because all you end up learning about your system is basically the real part of the impedance of your system, if you will. But if you have Poisson distributed charge carriers, you should get a phono factor, a noise as a function of current that in the high bias limit looks like 2EI. And if you had Poissonian distributed pairs of electrons going through, like you can arrange in certain superconducting experiments, you can get a phono factor of 2. And of course, if either the electrons were going through perfectly evenly spaced in time, or you had a continuous electronic fluid, so there were no discrete charge carriers, if you will, then you would have a phono factor of 0, right? So this is all for tunneling, these values of phono factor. But you can imagine, if I was looking at a strange metal, if there really were still quasiparticles, I might expect it to act very much like a phono factor of 1 if I was doing a tunneling experiment. If there were no quasiparticles, maybe I would see strongly suppressed noise. Now, for various reasons, it's easier experimentally not to try and do the tunneling experiment in this case. Also, I'm always a little concerned about the tunneling versions of this where effectively the only electrons you can ever remove or add to the system are whole electrons, right? Like free space whole electrons, if you're really pulling a charge physically out of the material. So a more interesting thing to do, I think, is to look at a constriction, look at a wire, a mesoscale wire made out of the material. So for a Fermi gas, this is all old news. Okay, this by old news, I mean it goes back, 26 years to the 1990s. So if I have a relatively short piece of some sort of a metal, what you expect if the device is short compared to the typical electron-electron scattering length, you expect the shot noise to be, the phono factor in this little constriction to be a third. There's a couple of different ways to derive that. You can get it from random matrix theory and Landauer-Bodecker formalism. You can get it from thinking about actually what's going on with electronic distribution functions. But the answer is, if I've got a diffusive metal and electron-electron scattering is weak on the scale of things traversing your wire, then the phono factor should be a third. If the wire is a little bit longer or the electron-electron scattering is a bit more enhanced, so that ends up being dominant, meaning that the electrons really share energy before they get out of the wire amongst themselves, then the phono factor is supposed to be square root of 3/4. And then for wires that are even longer, if electron-phonon coupling is important, then the noise actually gets really suppressed. So this is kind of the length dependence you expect to see, and this has completely been seen in ordinary metals, as I'll show you shortly, an example. So we wouldn't be able to do this experiment without these fantastic films that Silke already mentioned earlier today. So her group has been spending a long time, many years, figuring out how to grow almost perfect, almost strain-free ytterbium-rhodium-2 silicon-2 on germanium substrates. And this is from that science paper that she'd referred to, where they did the terahertz optical conductivity measurements. So if you actually have these films, you can now actually make nanostructures. Trying to carve something out of a bulk piece of crystal is actually very hard to do without damaging it to the point where its properties are very different. So again, my student Liang spent a long time figuring out how to do this in a nice way. This is a typical sort of process flow, right? You can put down some protective, you can put down some big thick gold contacts that are going to be your source and drain, if you will. You can put down a chromium wire that's going to act as your etch mask. You can do some etching using a mixture. Actually, I should update this. It's really more argon than SF6 at this point. But when you're all done, you can strip off the chromium with warm hydrochloric acid, and you're left with this etched wire and these big protected pads. We knew to use HCl because when people grow bulk crystals of ytterbium-rhodium-2 silicon-2, they use HCl to dissolve the flux metal that they use to do the crystal growth. So we know that the material itself is not harmed by HCl. So here's an example, and if you zoom in, you can clearly see, here's a little wire. The edges on the pads look a little rough on this particular one. But one of the important checks we did was we compared resistance versus temperature and resistance versus in plane, in this case, magnetic field, for the unpatterned film and the wire, to make sure that basically the patterning process, the etching, did not somehow screw up the crystal structure or the chemistry of the wire so badly that we were measuring something else. So what you find is that rho versus T is linear down to 2K as expected. The resistance is a function of field for in-plane field pointing this way, perpendicular to the wire, but in the plane is basically unchanged from the unpatterned film. So this is reassuring. It suggests that we are actually able to pattern this stuff and not ruin it. So what do we actually see? Here's, but before I show you the actual result, let me say, here's a comparison. Here's a little gold wire. This is actually a much better made, much more uniform gold wire than the one that was in the original preprint. I'm much happier with this one. It's much more uniform, and the resistance is very close to the resistance of the actual ytterbium-rhodium-2 silicon-2 wire that I'm going to show you in a second. But here you have a gold wire of kind of these mesoscopic sort of dimensions. It's kind of 80 nanometers wide and 500 nanometers long and kind of tens of nanometers thick, and with these big fat gold pads. And what you see is that the noise, and I'm plotting it as voltage noise because that's what we actually measure, but the noise as a function of bias current, and we've subtracted off here the Johnson-Nyquist noise, the thermal noise, right? Which is why the curves all start at 0. What you see is that the data are very, very consistent with a phono factor of a third. right? This has been seen by other people. It's now been seen by us in multiple different wires. If you go warm enough, here you are at 10K, you see the data points are a little bit below. In fact, if you go all the way up to 20 Kelvin, the phonon factor ends up being a little bit below a third, and we believe it's numerically, it makes sense that that's a bit of the onset of electron phonon scattering in the gold wire. Okay, so what about the ytterbium rhodium-2 silicon-2? This is the key result. What you find is that the noise in the ytterbium rhodium-2 silicon-2 is much, much smaller than, it's certainly much smaller than √3/4, which is kind of the value you sort of expect in this system where you believe electron-electron scattering is extremely important. It's smaller, considerably smaller even than F equals a third. And it's just very, very suppressed. It's not, it comes up a little bit as you get down to 3K, but really it's far below what you expect to see. Now, and we've seen this in multiple devices, and it's true in magnetic fields up to 9 Tesla, again, in plane field. Why is this true across all fields? Well, it turns out the non-Fermi liquid regime, the quantum critical fan for this material, by the time you get up to 3 Kelvin, it spans basically any reasonable accessible field. That tornado that Silke described, where it really necks down, that doesn't happen until you get down to dilution fridge temperatures. And it would be great to do these measurements in a dill fridge, but it is extremely challenging. There's a bunch of specific practical challenges for doing that. But these data right now, this is deep in this non-Fermi liquid regime. This is deep in this condo destruction critical regime. Well below the sort of the standard number of kind of 25 or 30K that people take for the condo temperature of the system. And we really see this dramatically suppressed noise. So you might ask, could this be due to electron phonon coupling, right? I mentioned that if you really crank up the phonons, basically what happens is that if you really crank up the phonons, then your electrons end up sitting at the temperature of the lattice, and you just have Johnson-Nyquist noise at the lattice temperature, right? Or something a little bit elevated relative to the lattice temperature. So you can calculate, this is kind of a simplified picture of electron phonon scattering, but you can actually, there's an experiment you can do to determine the strength of this electron phonon coupling parameter gamma. So for gold, just for reference, it's 5 × 10⁹ per Kelvin cubed per meter squared. This was, again, found in the 90s by Schonenberger's group at Basel. And if you have to be a little bit careful here if you're going to do this in our system, because the resistance itself is temperature dependent, right? Because we still have that linear and T temperature dependence, but you can do it. And we can, again, you're doing the problem correctly, and you can basically make a long wire, and you can look at how the noise in a very long wire behaves, and you can back out gamma. And so we've done this, my student's done this, make a 30 micron long wire. So really long, no shot noise issues here at all. This should just be essentially the integrated Johnson-Nyquist noise of what's going on in the wire. And if you can fit that noise extremely well to this model and back out a gamma, and it's a bit bigger. It's maybe almost a factor of 2 bigger than for gold, but really it's the same order of magnitude as for gold. Okay, and you can use that gamma now to calculate what you think the differential resistance should be if all of the nonlinearity you see is due to heating. And qualitatively it gives you the right answer, but it suggests there is probably some intrinsic nonohmic response in the material. But the bottom line is, if gamma is this big, that does not explain the suppression, right? You just can't get there. In order to get noise as low as we see, you would have to have a gamma that's like almost 70 times larger than the value in gold. So we're way off. We're like 35 times too small based on the experimentally determined gamma, right? So we really do not think that the noise suppression in YRS in ytterbium rhodium-2 silicon-2 is due to phonons. So it's not due to phonons. You might also ask, do non-ohmic corrections matter, right? The fact I alluded to the idea that there's some non-ohmic response. There's some differential resistance that has a bit of a bias dependence, some of which is from heating, but not necessarily all of it. Does that matter, right? So it turns out there are people who have worried about how do you think about the thermal noise from non-ohmic devices, and you can go and try and apply this, and just you can fit things with various complicated expressions. So here's what our fits look like that I already showed you that don't worry about the non-ohmicness, but here's what the fit looks like if you worry about the non-ohmicness. And if you carry this out, so here's, the point is the data themselves are just small. The noise is just small. The system is quiet. This analysis about non-ohmic stuff just has to do with exactly what phono factor number you pull out of the calculation. And you can include that second order correction and the fit quality looks basically the same. And in fact, what happens is if you include corrections for nonlinearity, like if you're very conservative and assume all the nonlinearity, all the non-ohmic response is really intrinsic to the device, and you go forward with that, you can still fit the data, and what you find is the phono factors are actually even smaller than what we saw before. It's just a question of what number you pull out of your fits, right? The data points are the things you should really pay attention to. The data points are what's determined by the experiment. So another possibility, could the suppression be due to Fermi liquid effects, right? And Chi-Miao just talked about this in the previous talk. Yiming and collaborators, they've really worked this out. It's a result. It's a little surprising that this result, as Chi-Miao said, that this wasn't figured out a long time ago. But the bottom line is, if you take a Fermi liquid and you allow for kind of very almost arbitrarily strong renormalization of the quasiparticles, but you make sure the quasiparticle weight doesn't go to zero, the Landau parameters end up canceling when you do the calculation. The quasiparticle weight itself never appears in the final result, and you expect a strongly correlated Fermi liquid to have a phono factor that approaches √3/4, and that is totally not what we see. Therefore, it's very tempting to think, okay, it's not due to phonons. If there are any quasiparticles at all in this diffusive thing, you should still get √3/4. And we see this drastically suppressed noise response. It is reasonable to think that maybe we're in the limit where there are really no quasiparticles. Maybe the charge is transported by some collective many body response of the whole electronic system. Now, the fact is that the phono factor does go up a little bit as you cool down, and that's not necessarily surprising. If there are any dispersing features left in kind of the spectral weight at all, even if there isn't a quasiparticle peak, if there's any dispersing features, they'll kind of tend to sharpen up as you get colder. And they, you would only expect a true zero for the phono factor if the spectral function was completely flat and absolutely featureless. So that's kind of where we are. Again, you can think about this in terms of distribution functions as well. This is not a super well-developed cartoon here, but I think the idea is that, whatever my distribution function is, which does not have any kind of little vertical step that would indicate quasiparticles, my strongly interacting, highly entangled system is going to have some distribution function that if you really knew the microscopic theory of the strange metal, you could compute what this is, and then you could go and you could compute what you think the noise should be, right? The bottom line is that as of now, there is not a theory in the literature that talks about what you should see in a strange metal if you do a noise measurement. I know there are people working on it, and I'm very excited that people are working on this. But with that, I guess I'd like to summarize, and I'd be happy to take some questions. So, shot noise provides a comparatively direct quantitative way to characterize the charge carriers in mesoscopic systems. Initial measurements in terbium-rhodium-2 silicon-2 show really suppressed noise compared with any reasonable expectation for a Fermi liquid. And we can rule out phonons as the cause of the suppression because we can experimentally measure what we think the phonon coupling is. Fermi liquid effects should not be responsible for the noise suppression rigorously. And so the only other game in town, as far as I'm aware, is that they're really, we really need some kind of microscopic theory to understand how to compute noise in a system where there are not these well-defined quasiparticles, because that I think that's how I would intend to interpret the noise suppression. And of course, there's a lot of things left to do. It would be great to look at other strange metals and see if this noise suppression is a universal response. It would be great to look at very low temperatures and really try and do field tuning. That'd be fantastic. So we got our work cut out for us, but I think already where we are, we can make very strong statements that this system is weird. It is in terms of the noise, it is quiet, and I think that's pretty exciting. So with that, I'll put up the acknowledgements again, and I'd be happy to take questions. I realize I kind of sped through that at warp speed, but I'm happy to take questions if people have any.
Thanks, Douglas. Beautiful talk and data. Questions? Yes, Hanyu.
Hey, Doc. Yes,
Hey,
it's a very exciting talk. So I always had this question I want to learn because you explain more on the phonons. The T over T to the 5 order, that page, you mentioned that we get the gamma and it's not phonons. Is there an intuitive picture of how phonon can smear out the noise?
So I kind of rushed through this. I apologize. So if you think about it, there's a few different ways to think about it. If you want to, probably the simplest thing is to think about the limiting case. Imagine that the charge carriers talk to the phonons all the time, right? Very, very strongly. Well, then they're all that's ever going to happen. You're not going to have any of these. In some sense, you're not going to have any non-equilibrium effects of bias at all. All you're ever going to see is a system where the carriers are basically in thermal equilibrium with the phonons at the lattice temperature, and that's it. So then you'd only ever measure Johnson-Nyquist noise. And all of this shot noise stuff is also sometimes called excess noise, because it's noise above the thermal noise. So in the limiting case where the electron phonon coupling is very, very strong, then the electrons are just coupled to the lattice and are in thermal equilibrium with the lattice. Now, the intermediate situation is a little trickier, right? I mean, having some kind, there's various derivations of the noise that kind of keep track of the flow of energy between the carriers. And in some sense, in the Landauer-Budiker picture, things work out kind of cleanly if you've got a small number, if you're looking at individual channels, because you can talk about, an electron can either be transmitted or reflected, right? And you can have energy transfer between electrons, and that's okay because it can affect, the net. This doesn't really change anything. But if you allow energy to leave the electronic system entirely, then this whole derivation of noise from that picture doesn't work anymore. So I hope that was helpful.
So if we make it generalized, then this increased shot noise is a signature of non-equilibrium behavior, or can we say it's a signature of some coherent wave function behavior?
There doesn't have to be a lot of coherence going on here, but there has to be some, yes, it's an indication that you're driving the electronic distribution function out of equilibrium.
Got it. Okay.
Yeah.
Cool. Thank you.
Mm-hmm.
Any other questions? Just a quick one for me. Douglas, could how would a viscous flow regime manifest in an experiment like this? That's maybe a bit off topic or off the wall.
So you mean if we're in this hydrodynamic?
Yeah, strong momentum conserving scattering going on.
So I think let me think carefully about that. So I think if underlying all of this, you still have quasiparticles, you should get the √3/4. Because the only assumption that really goes into the √3/4 is that you've achieved some kind of local effectively some local effective temperature, right? Where the electron, I mean, maybe that shows up in my this cartoon here, right? So in the phonon factor equals the third case, if you look at the midpoint of the wire, the distribution function ends up having some funny two-step structure, right? And that's the thing that ends up giving you the 1/3 in some sense. If you let the electrons smear themselves out energetically, you get this some effective local elevated electronic temperature, and that'll give you the √3/4 case. And so I think the hydrodynamic aspect is kind of kind of part of that. If it was just hydrodynamics, I think you'd still get the √3/4.
Right. Thanks. Perhaps the last question from Taran.
Thank you. Yeah, a very nice talk. I haven't actually thought through this much about short noise, but my question is, if the width of this constriction becomes, eventually if it becomes very small compared to, let's say, any scattering and scale, wouldn't you start seeing one-dimensional physics in a, suppose I take any two-dimensional system and cut out just a 1D wire?
You're absolutely right that so excuse me. So eventually you have to start worrying about confinement effects. That's right. So these wires, I should have said, I mean, the scale of these wires, I can go back to an actual electron micrograph. Here we go. So, this stuff, it's small, but it's not that small, right? So the typical length of one of these wires is a few hundred nanometers. The width is a couple of hundred nanometers. The thickness is about 60 nanometers. So you're pretty far away from any, the band structure is effectively still 3D.
I see. Okay. Thank you.
But you're right. I mean, if you really confine things down to very, very tiny scales, you have to worry about this stuff. That is absolutely true.
Can I ask just one other question? Maybe if you don't have time, I can just stop. I can email you, and it depends on
Or a quick one.
I guess so the claim is, if I take any essentially standard quantum phase transition, you should see this, right? It doesn't have to be, quasiparticles don't exist in most, at any non-Gaussian phase transition, this should be true, if I understood it. Suppose if I consider this Dirac electrons, let's say consider the antiferromagnetic to semi-metal transition in some Dirac system, even there this should be true. F should be basically 0.
Well, I think it's tricky. I think I don't know, Chi-Miao might be a better person to answer this. I mean, my interpretation would be, you have to base it to really get a very small phonon factor. You kind of have to kill all quasiparticles across the entire Fermi surface.
Sure,
right?
sure. Yeah.
Like I think if there's any surviving quasiparticles, you're going to see something in the noise. So
if I can just,
yeah.
No, I would add to what Doug said. I mean, Taro, as you know, in this Hertz-Millis type of picture, when you have a Fermi surface, not Dirac point.
Yeah, no.
Much of the Fermi surface
would
be cold, right? So there's no T-linear resistivity, and you can, and short noise would also be capturing the quasi-particle contributions, because those are the current carriers.
I agree. Yeah, in the Hertz-Millis, I agree. I was just thinking this is even if I just take a relativistic phase transition between, let's say, a semi-metal and some, let's say, antiferromagnet, just some Gauss-Neibel transition, then it should be more like this. It should be 0, I guess. Thanks.
All right. Well, let's thank all the speakers again. That was a lovely collection of talks.